rectangle attacks. In this session, we have two talks. The first talk is new properties of double boomerang connectivity table. The authors are Qian Yang, Lin Song, Siwei Sun, Danping Lei Hu. The speaker is Qian Yang. Welcome.
Hello, everyone. My name is Qian Yang. I come from Institute of Information Engineering. I appreciate this opportunity to make the presentation. There are 5 parts in my presentation. The first one is the preliminary. It is known that boomerang attack is one variant of differential attacks. And the aim of it is to construct a long differential by using 2 short ones with high probability. And there is an assumption that the 2 trails are independent. Then researchers focus on the dependency between the differentials. A sandwich attack was proposed. Sandwich attack divided the cipher into 3 parts, E0, EM, and E1. Sandwich attack handled the dependency in the middle part, EM. Now let's review some definitions used in boomerang attack. DDT is usually used in differential attacks. DDT alpha1, alpha2 means the number of the pairs satisfying the conditions that the input difference is alpha1 before the S box and the output difference is alpha2 after the S box. BCT is the boomerang connectivity table, and BCT alpha1 beta 2 is the number of the quartets satisfying the conditions that the input difference in the upper pass is alpha1 before the S box, and the output difference is beta 2 in the lower pass after the S box. Compared with BCT, the UBCT as one condition in the upper pass. So UBCT alpha1, alpha2, beta 2 satisfying 3 conditions. Similarly, LBCT, the lower BCT, it is the number of the quartets satisfying 3 conditions that there as one condition in the lower pass. EBCT is the extended BCT. It is the number of the quartets satisfying the 4 conditions. So all these tables are for one S box. In boomerang attack, in the EM, there are always some rounds. So how about 2 continuous S box or 3 or T continuous S boxes? First, we give the definition about the double boomerang connectivity table. Look at the figure. Alpha1 and alpha2 are the differences in the upper pass for the first S box, and beta 2 and beta 3 are the differences for the second S box in the lower pass. DBCT alpha1 beta 3 is equal to the sum of the lower DBCT alpha1, alpha2, beta 2, and beta 3, where the lower DBCT is equal to the UBCT times the UBCT for the first S box and times the LBCT for the second S box. From some DBCT, we find that for all S boxes, non-zero DBCT occurs mainly when alpha2 is equal to beta 2. That is, in the DBCT, there are mainly lambda switch and S box switch. Especially for some S box, there are only lambda switch and S box switch. That is for all alpha1 and beta 3 this equation is true. And from the equation, we can obtain a relationship between DBCT and DDT. And it also reduces the time complexity for DBCT from 4 dimensions to 3 dimensions, such as the icebox of present L block, MIPS, and twin. All these icebox are hard. And for others, such as Craft, Skinny, Pride, Calmer, they are general icebox. Next, I'll show some extensions of the property. The first one is for a hard icebox, not only DBCT, but also TBCT, the equation is always true. So for TBCT, there is always a relationship between the TBCT and the DDT. The second one is we get some property about the block ciphers with complex linear layers, such as the AES. This table shows the number of entries for each value for the DBCT IG used in AES and the basic DBCT for the AES. From the table, we can find that the basic DBCT, the icebox of AES is hard without 0 values, and DBCT IG with the complex linear, most values are 0. This point observe our attentions. Now let's see some application of the new property. The first one is through the same Boomerang distinguisher with a different icebox, how DBCT uniformity and hard icebox matter. We take the 7-round distinguisher of Craft as an example. This table shows the property of the distinguisher with the different iceboxes. From the table, we can find that Craft and the present share the same DDT and BCT, but present has a better DBCT than Craft, and the icebox of present is hard. The result is that present has a lower probability than Craft. Calmer has a better BCT than present, but present with a smaller DBCT. And the icebox of Calmer is general. The result is that present has a lower probability. These 3 iceboxes share the same DDT, BCT, and DBCT, and all of them are hard. So the result is that they have almost the same probability. MIPS and the twin have the smallest BCT and the smallest DBCT, and both the icebox of them are hard. The result is that they have the lowest probability. From these observations, we find that apart from the uniformity of BCT and the DDT, the uniformity of DBCT is a new measure criterion to evaluate the performance of icebox. And then the second application is that for the AES, the DBCT with complex linear layer has too many 0 values. Inspired by this, we recompute some distinguishers about the block ciphers based on AES, such as tweet AES and the deoxys. We found that 3 distinguishers of them have 0 probability. So that is for a hard icebox with a complex linear layer should be treated carefully. Then I'll give the MLP model to search for the Boomerang with the cluster probability briefly. In the previous works, there are always two steps to search for the Boomerang distinguisher. Step one is to search for good truncated Boomerang characteristic with the least active S boxes. And step two is to search for the best instantiations. In our work, we give a formula for the probability of clusters firstly, and then give a new MLP model to search for good clusters directly. In E0 or in E0 or in E1, we use the numbers of cells which need to be zero from uniformity to describe the probability. And in EM, we use CM to describe the probability, where CM is the sum of the number of cells which need to be zero from uniformity. The number of UDDT2 and LDDT2, the number of MBCT and the number of BCT. For example, use our formula, we can give the conditions for the 13-round distinguisher of Kraft. The result indicates that the conditions are closely related to the actual probability. Then for the MLP model, we give some rules about the attribute propagations through these operations, such as the sub-bias, the XOR operation, and the rule of modeling of the table and modeling of the upper and the lower boundary. The objective function is to minimize the number of conditions, and we use the new MLP model. We get two new Boomerang distinguishers of Kraft with a higher probability than before. Now this is the conclusion. At first, we give some properties of DBCT, such as the Lander switch and the S-box switch happen in most cases for all S-boxes. And for hard S-box, only the Lander switch and the S-box switch are possible. These properties tell us that the DBCT is important to evaluate the performance of S-box, and hard S-box with a complex linear layer should be treated carefully. Second, we give an MLP model to search for the clusters. At first, we give a formula for the properties for the probability of clusters, and then we give the model with the cluster probability. Thank you for your attention. That's all.
Thanks. Any questions?
I have a question. On page 10. On page 10.
Okay.
I wonder if it's possible that the alpha 2 on the left can be different from the alpha 2 on the right. Just at the middle part of the picture. And at the same time, the beta 2 can be different from the beta 2. The beta 2 in front can be different from the beta 2 in back.
Yeah. But there is assumption that the two the opposite sides are equal. They in actually beta 2 can they are not in actually beta 2 and beta 2 yeah, they are not is not equal to beta 2 EP. Just in our work, we have the assumption that the two sides are equal.
Okay, okay. Thank you.
Thanks.
On page 26, two AES and deoxys are all AES-like ciphers. So I would like to know, besides AES-like ciphers, does incompatibility exist in other ciphers?
Yes, it is possible. For these S boxes with the property, it is maybe for other as block ciphers.
Okay, thank you.
Hi, thank you for your presentation. I was wondering, did you try to use the MILP on Skinny? A similar MILP model on Skinny?
Sorry, pardon?
Did you try to use the MILP on Skinny?
Yeah. I have tried to apply the model to Skinny, but the result is that we didn't have the more lower probability, so we didn't show this result.
Okay, thank you. And on craft, more than 10 rounds, did you find any distinguisher, or was it the same than in the literature? Did you apply it on craft more than 10 rounds? Because you have found...
Yeah. We have we have tried to try applying the model to the distinguisher more than 10 rounds, but it's also we didn't get the good results.
Okay, thank you very much.
Thank you.
Oh, hello. In my understanding that the DBCT has a strong connection with the linear layer in a cipher, and the best suitable situation, I think, is if the linear layer is a binary matrix. But for the bitwise permutation and even the MDS matrix, I want to know that what's the advantage of the DBCT over the BCT, UBCT, LBCT framework. Thank you.
Firstly, for SBox, DBCT is equal to UBCT times LBCT, and there are 4 dimensions. But but we can use DDT to compute DBCT with only 3 dimensions. So the first, it can reduce the time complexity. And for general S boxes, the equation is always true. So And in DBCT, the lower DBCT occurs mainly when alpha 2 is equal to beta 2. So we can also use DDT to replace DBCT with some if in many distinguishers, the compute is very complexity. So sometimes it may sometimes it is too huge to compute the probability. So maybe use the DDT to replace DBCT. Now we can get the probability in a short time.
Okay, is that we transfer the DBCT to the DDT under the hard icebox assumption?
Yeah.
Okay, and the next question is, have you tried to consider the DBCT value, entry value in the MLP model, or even the specific value of the DBCT? And because I noticed that the MLP model you present that only focus on the BCT, OBCT, and UDDT.
Yeah, the MBCT includes the DBCT, and we consider the DBCT in our MLP model.
Okay, and the last question is there any connection between the boundary of AI and the DBCT and the maximum number of T in the TBCT?
Sorry, pardon.
I want to know, is there any connection between the boundary of EM and the maximum number of the TBCT of a specific cipher?
Yeah, for a hard icebox TBCT, this formula is always true. We can also use DDT to replace the TBCT.
Okay, thank you.
Thank you.
Okay, I think we don't have time for further questions. Thanks, Qianxian, for the talk. Let's start the next talk.
Thank you. Thank you.
The next talk is that aided automatic search for Boomerang distinguishers for ARX ciphers. The authors are Da Chao Wang, Baocang Wang, Siwei Sun. The speaker is Da Chao Wang. Welcome. Yes.不是这个，是一个 PDF， 这个吧，是吧？对。这有一个，
Hi everyone, my name is Wang Dachao. My report is about set-aided automated search of Boomerang distinguishers for AI ciphers. This is a joint work with Wang Baocang and Sun Siwei. Boomerang cryptanalysis is a technique to connect to short differential characteristics to form a new distinguisher covering more rounds. The whole cipher is separated into two parts. For each part, a differential characteristic is applied. Then under an independence assumption, these two characteristics can be connected like this figure. Then, however, previous work found that this assumption may not always hold, and several techniques were proposed to fix this problem. One of them is the sandwich framework, like this figure. In the middle, a new part is separated out, called switch, and denoted by EM. Special cryptanalysis is put on this part to analyze the connectivity of the characteristics. Typically, the cryptanalysis on EM is reduced to that on the nonlinear operations. For SPN ciphers, it is reduced to the cryptanalysis on the S-box as this scenario. Since the S-box is typically small, we can enumerate all of its inputs, and the result is a new table called Boomerang connectivity table. And in 2020, researchers found that we still need more variants of the BCT, which are the UBCT, LBCT, and the EBCT. Up until now, the cryptanalysis on S-boxes are quite rich, but what about the Boomerang connectivity table on the other nonlinear operations? In particular, we are thinking about the BCT on the modular addition. To the best of our knowledge, there is only one previous result, but the definition of this BCT is given without many details. And it is also claimed that the difference nabla, it is the one below the figure. It is claimed that this difference must be 0. But however, in our work, we noticed that if we view the modular addition as a special S-box like this red equation, all the previous techniques on S-boxes can be applied here. And the formula is as below. You may see that this formula depicts a very large BCT. It has 4 dimensions, with each dimension has size maybe 16 bits, 24 bits, or 32 bits. So to computing the whole BCT, it would be impractical and sometimes infeasible. So we are thinking about, is there a fast method to compute one arbitrary entry in this BCT? If so, can we construct set models for it? And furthermore, are there any new results on the AI ciphers? Based on this motivation, our contribution separated into 3 parts. First, we design a dynamic programming algorithm to efficiently compute the tables. Second, we construct set models for these tables. And finally, we tag Spec and Lee as examples and improve the previous results. Okay, let me introduce the computation of the BCT. During the computation, there are 2 important equations here. They depict the relation between the modular addition and the XOR operation. Here, I want you to focus on the recursive definition of the carry function. For example, the carry 0, the ith bit of C only depends on the previous bits on X, Y, and C, so does B. This is an important property for our algorithm. With these 2 equations, we can rewrite the definition of the BCT into a much simpler form. with this new definition, we have two observations. The first observation is that every this equation is a restriction on the I-1 bit of L and R. But what about the N-1 bit of L and R? The answer is they can take arbitrary values because this is the only restriction derived from the definition. The second observation is that the 4-bit string can only take 8 possible values. Here I concatenate the 4 carry bits into a 4-bit string. Based on these observations, we can partition the definition of the BCT into several subsets by the values of the bits of L and R and these 4-bit strings. Since every values of the bits of the LR are valid, so we can sum up all of the cases into a new form. Here we define the new function f to represent the rightmost part because the original part is too complicated. Okay, now our goal turns into how to compute the function f. A trivial idea is to partition the function f again by these values. But this time, we notice that some of the values of the N-2 bit of L and R could be invalid. So we define the new function g to denote whether the chosen value of these 2 bits are valid or not. With the function g, we can continue to sum up all of the cases. And now the computation becomes this. Again, we define a new function t to represent the summation of the function g. Here, I want to note that the function t can be pre-computed because its input is only 2 4-bit string and another 4-bit values. And you can see, again, we have a recursive definition of the function f. And this is very perfect for a dynamic programming algorithm. If you are not familiar with this kind of algorithm, you may think about the computation of the Fibonacci series. The computation are the same. Before showing our algorithm, I want to note another important property we found. It is symmetry in the computation. This symmetry helps to reduce the time complexity of our algorithm. Okay, here comes our algorithm. Line 8 conforms to the summation in our formula. And then we found a way to Booleanize this algorithm by if the value of t is non-zero, then we define a new value of tb to be 1. If the value of t is 0, then we set a 0 value tb. With this modification, we obtain a new computation of f as the below one. This equation contains only Boolean operations. And this equation can check whether the function f is non-zero or not. Based on this new computation, we modified our algorithm. You can see the line 8. Line 8 also conforms to the max operation in this formula. This algorithm is able to check whether the BCT entry is non-zero or not. This is our first step into Booleanize the computation. And Booleanization is important for set models. Furthermore, we want to control the computation further. We found another important observation. For all u in this set, if the value of t is not all non-zero, then we have another recursive definition of the summation of function f. Please remember that the computation of BCT is also the summation of function f. So based on this observation, we derive a heuristic trick. I call it partial BCT. If k out of n minus 1, these equations are required to be satisfied, the resulting BCT entry would be 4 to the power of k plus 1 times a number q. That is, we just express this red sentence as Boolean expressions, a k of them. This idea comes from the partial DDT by the previous work. With this partial BCT, we are expecting cancel out the small values in the BCT and obtain a size reduced BCT. But however, the fact is that currently we lack enough knowledge about the number q. Second, the resulting partial BCT still contains small entries. But luckily, our experiments show that the model always returns BCT entries with value around 4 to the power of k plus 1. This is enough for us to construct the set models. Here comes our complete model. Based on the previous algorithm, we model line 8 as the first Boolean expression. For line 10 to 13, we create another Boolean operation, Boolean expression. And the heuristic trick is applied to the first Boolean expression. I want to know that our model cannot return the exact value of this entry. It can only select arbitrary entry in the BCT. So the previous searching model cannot apply it here. So we have to come up with another new searching framework. Our first framework aims to find Boomerang characteristics with high probability. We just tweak the thresholds in the switch, that is the size of the partial BCT, and then search the characteristic until we found the desired characteristic. This framework is fast, but may miss some better characteristics. Our second framework is quite complicated. We first set thresholds to 0. That is, we consider the whole BCT. And then we found the upper bound of the probability of the Boomerang characteristics. Then we tweak the threshold again, and this time we also tweak the upper bound of the probability. Then we enumerate all the characteristics and count the number of the characteristics. Then we return the largest cluster as the result. Due to the enumeration, this framework is slow, but can take the advantages of the clustering effect. This is our result. We found current best Boomerang distinguisher on spec 32 and spec 48. We also fixed the previous probability estimation of Lee. You can see in this table 5, AIX tools return the precise result in a very short time, much faster than ours. So we do a comparison. The first result is that you may think that our algorithm is very similar to the AIX tools, but they are in fact constructed from 2 different perspectives. Our perspective reveals more mathematical properties behind the modular addition, which are not published before. As you have already seen, AIX tools is faster and more precise. And finally, also the most important thing is that our technique is capable of searching characteristics, while AIX tools cannot. Okay, let me do a conclusion. In this work, we accomplished 3 results: the efficient algorithm, the set models for this table, and new results on these 2 ciphers. but there are also some limitations on our technique. The first one is that the current computation of the tables are not quite convenient, are not very convenient to be modeled. If you look into my code, you will find that our model is quite large. So the current models for the switch are too large. If we want to search some complicated cipher, the model would be infeasible. And third, the optimal distinguisher are still unknown because our technique is a heuristic technique. And finally, comparing with AI tools, our computation of the probabilities are slow. All the codes are publicly available at my GitHub repository. You can download the code here. Thank you very much for your attention.
I think we don't have time for further questions. Thanks, Dr. Wang, for the next talk. That's the end of the session.
对的。